In this video, I introduce DINO-WM models on pre-trained visual features enable zero-shot planning. DINO-WM model models the dynamics of an environment as a partially observable Markov decision process defined by the table O, A, and P, where O is the observation space and A is the action space. The dynamics of environment is modeled by the transition P, which predicts future observation based on the past actions and observations. The DINO-WM model is trained on pre-collected offline datasets and then uses the trained world model to perform visual reasoning and control at a test time. At the inference, DINO-WM model starts from arbitrary environment state 01 and is provided with goal observation in the form of RGB image, and is asked to perform a sequence of actions from A0 to AT to reach the goal state OG. As shown here, during training, we train the world model on pre-collected offline trajectories. The pre-trained DINO-W2 is applied to find the dynamics of environment. This is a test time inference. At the inference, given a target observation OG, the trained world model optimizes the agent behavior by planning through the model using model predictive control. DINO-WM model consists of three components, namely observation model, transition model, and optional decoder model. Whereas the observation model encodes image observations O to latent states Z, and the transition model takes in a history of past latent states Z. The decoder model takes in latent state ZT and reconstructs the image observation OT if necessary. The training objectives for the decoder model is independent for training the rest part of the world model. As shown here, we use a pre-trained DINO-W2 model to map the observations in physical world and the goal observation in the physical world into the latent space, and then the transition model, namely the vision transformer, use the action produced from the model predictive control model and the past states as an input to predict the future states. A causal attention in vision transformer is implanted to predict latent representations autoregressively at a frame level. Each action vector mapped from the original action representation using a multiple layer perceptron file to each patch vector. DINO-WM model is trained using a teacher forging as shown here. During training, the trajectory is sliced into segments of length h+1, and the latent consistency loss on each of h predicted frame is computed by using this formulation. Here is a detailed information of the transition function. Now we use the training frames and the actions together as an input to the vision transformer with a causal mask as shown here to predict the next frame. To evaluate the quality of the world model, the trajectory is optimized at inference time. For example, DINO-WM model receives the current observation O0 and goal observation OG, both represented as RGB images. The planning can be formulated as a process of searching for sequence of actions that the agent will take to reach OG. Model predictive control is applied to facilitate planning by considering the outputs of future actions. The cross-entropy method is used to optimize the sequence of action at each iteration. The planning cost is defined as the mean squared error between the predicted latent state and the goal's latent state, given by here and explained in this figure. This image in the physical world. We predict the future images in the latent space. Since the world model is differentiable, the gradient descent can be applied to optimize this objective, which allows the world model to directly guide the agent toward a specific goal. For more details, please check